Hi everyone, my name is Emmanuel Raguel. So today I'll be talking about a problem we all know too well, that frustrating moment when your video freezes during the best part. So I'll show you how we use SDN, which is software-defined networking, to fix this problem. So we look at SDN as a given networks a brain that makes smart decisions in real time. Over the next few slides, I will walk you through the key part of our project. So first, we're going to start by introducing the project, the goal, and why this matters. And then I will walk you through how we set our test environment, and you will see how we build the network topology using mininets. And then we will cover how we prepare the video content for testing and how the SDN controller setup comes next, the brain of the operation. We will then dive into our actual bandwidth experiments. You will see how we monitor network performance in real time. And finally, we'll wrap up with what we discover, the structure. We'll give you a clear view of how SDN can optimize video delivery when network condition changes. So our core focus was investigating how SDN technology can enhance adaptive video streaming performance, particularly when dealing with fluctuating network bandwidth. So what exactly did we build? We built a system that automatically adjusts to video quality based on network conditions. It's kind of like how your eyes adjust to dim lights. And our four main goals were to making the network self-aware of video traffic, test it under real-world bad connection, build a local network in our lab using Mininet, and then finally using the same tech as Netflix, which is the dash.js. The key tool we installed were Mininet for network emulation, Open vSwitch for virtual switches, and Apache for our web server, and Fairpeg for video processing. And we install JPAC for generating the streaming packages. The installation process was well, done using these two commands. And then finally, we test the version of Mininet and Open vSwitch using this command. Here, we created a simple but effective theory switches linear topology using Mininet Python API. The key components are TV switches connected in series, host 1 as our video server, and host 2 as the client device. The most important part is the bottleneck link we intentionally created between the switches S2 and S3. We configure it with just 10 Mbps bandwidth, 30 milliseconds of delay, and 1% packet loss. This simulates real-world network congestion. Uh, when we first tested the connectivity with the SDN controller, all the packets were dropped as expected. But here, where it gets a little bit interesting, after starting the ROI controller, we achieved zero packet loss. This clearly shows how SDN can dynamically route around problem area in the network. We launched the topology using a customized miniline command that enabled traffic control on our link. The before and after ping text really highlight SDN value for maintaining connectivity. This all run on Python code that's surprisingly, I wouldn't say simple, but still, yeah. But we created switches with ID tags like license plates, and that we gave our streaming houses IP addresses, and we set the road between them. Most at just 100 Mbps with one intentional bottleneck. The entire setup fills in about 20 lines of code. The link were carefully set up to stimulate real-world condition, save an edge link at 100 Mbps, for normal connection, a constraint 10 Mbps bottleneck between S2 and S3, which is the switch 2 and 3. We added 30 milliseconds delay and 1% packet loss to the middle link to emulate one condition. The typology dictionary at the bottom allows Mininet to recognize our customized setup when launching when we launch the environment. So now let's look at how we prepare our video content for adaptive streaming. We started with a common text video, the big buck bunny. As we used this sample, which we downloaded directly to our server. For our streaming text, we needed multiple quality versions of the same video. Using the FempEg, we created three different encodings at varied bit rates. For example, the first one, which is the 480p version, we encoded at 800 kbps with scale dimension of 854 by 480 pesos. And the key step was generating the MBD file, that's the media presentation description, that tells the player about the available streams using the MP4 box. We created the manifest file with a 4-second segment duration, which enables the dash player to switch between qualities smoothly during playback. This presentation work was kind of crucial because it allowed us to test how effectively our SDN system could adapt to changing network condition by switching between the different quality streams. So after preparing our multi-bitrate video file, we generated the MBD manifest we needed to make the content available through our web server. Uh, but by doing this, we first of all we created a dedicated directory in Apache Web Root for our Dash content. We moved both the manifest file and all the encoded video segments into this location, and then ensure proper permission was set for the web server to access this file. We double check the Apache main type configuration to generate proper delivery of our MPEG dash content. This is crucial because the browser needed a MIME type of handle adaptive streaming properly. And then finally, we verify everything by using this code. We verify everything was working by testing the local area of the manifest file. The code command the code command confirm our Apache server was correctly serving the dash content before beginning our Ultra streaming tests. The deployment process ensure our video content is properly structured and accessible for the adaptive streaming experiments we will conduct with our SDN setup. So here we began by activating our Wire virtual environment and verifying the controller version. The simple Switch 13 application gives us basic OpenFlow 1.3 support, while our customized dash monitor extended, uh, extends this video streaming awareness. Key operational commands include starting the controller in verbose mode to monitor decision, check the installed OpenFlow rule or switches, and lastly, examine switches connection and data path IDs. Retrieving real-time flow statistic, as well as retrieving real-time flow statistic through REST API calls. The REST API interface run on port 880, giving us visibility, which give us visibility into active switches in network, pair flow statistic, current forwarding rule. The combination give us both control and visibility, letting us to see exactly how the SDN manages our video traffic while allowing us for dynamic adjustment. So here we taught our controller to recognize video streams, like training a dog to fetch for a specific toy, whereby the Python code listen for new packets, check where they come from, which is the switch they're coming from, and then log the activities. Here we conducted controlled experiments to evaluate how our SDN enhanced adaptive streaming performance under different network conditions. The first one, which is the bad connection, is like a, let's say for instance, a small crowded cafe Wi-Fi, which is the TV buffering spin, which is our very first one, which is the 480p. And then the second one, let's say a decent connection, 5 Mbps, which is our home Wi-Fi. Very rare, a rare buffering. It's not too bad, but still. And then lastly, we have the great connection, which is the 10 Mbps, flawless, 1080p. The SDN controller acts like a smart assistant, always picking the best quality your connection can handle. For each test case, we use hypo to artificially constrain bandwidth and then monitor the dash player behavior. Here, our REST API provided real-time visibility into network performance. By querying flow statistics, we could see exactly how video traffic was being routed through SDN. The results speak for themselves. You can see here the first one without SDN buffering occur frequently as the network struggle with congestion. The second one without with SDN, our controller dynamically optimized VAT based on live condition. The outcome was 53 reduction in buffering, in fact, proving that SDM real-time monitoring and adaptive routing directly improves streaming qualities. Key takeaway: SDN transfer video delivery by monitoring flow in real time and optimizing routes. It reduces buffering and maintaining quality even under challenging network conditions.